Good morning, everyone. I'm Kosalaya Pandar, a blockchain researcher at National University of Ireland in Galway. I'm going to talk about enrichment of blockchain transaction management with semantic triples. If we talk about public blockchains, they are optimized for transparency. Therefore, managing private and sensitive information in public blockchains is a challenge. However, when we consider private permission blockchains, they separate transactions as private transactions and public transactions. If we consider an enterprise transaction, you always find the public information and private and sensitive information. So private permission blockchains separate these public information and private information as two different types of transactions and treat them separately. However, this separation removes the cohesiveness of information in a transaction, and that leads to so many other problems when it comes to auditing, traceability, like applications where you need to process both public and private informations together. Let's consider transactions invocation in public blockchains and permission blockchains. If I consider public blockchains first, here we can see a user creates a transaction, verifies, put the signature, and broadcasts the transaction to the entire network. Then the nodes in the network verifies the transaction, and miners they create blocks and trying to solve the proof of work. And then when they find valid blocks, they broadcast valid blocks to the entire network again, and then at the nodes they verify the valid blocks and update ledgers, and then the transaction is completed. Now in this kind of an approach, there is no central authority. It has decentralized governance and no single point of failure. Transactions are transparent, but trust is distributed, and distributed nodes allow reliable access to information, and there's no double spending. And if I come to permission blockchains, now only permission members can be part of the blockchain network. So the client creates a transaction and sends the transaction to the peers. Then at peers, they verify the transaction. They simulate the world state with the transaction, endorse the transaction, and sends this transaction back to the client. And at client is checking all the endorsements, and then client will send those transactions to the orderer. The orderer verifies the transaction and create blocks and sends those blocks to all the peers. And at peers, then again they simulate the world state and then update their ledgers, and the transaction will be completed. And however, in this kind of permission blockchains, especially in Hyperledger Fabric, they used technologies like Kafka, Solo, or Byzantine fault tolerance to implement the orderer. They're trying to use clustering based approaches, but because people are complaining that there's a possibility of single point of failure at orderer, and also in permission blockchains, like only the permission members can be part of the blockchain network, so the governance is not distributed in these type of approaches. In this research, we are focusing on how to improve the cohesiveness of blockchain transaction information. A blockchain transaction can have both private and public information, and permission blockchains separate this information, create public and private transactions, and process them separately. This separation weakens the cohesiveness of transaction information and develops an extra burden when it is necessary to connect both public and private information. For example, when you need to do auditing, you need to process both private and public information. On the other hand, semantic triples, they connect subjects and objects using predicates. For example, if you see this example, the Bob is a friend of Alice. Bob is a person. Bob is born on 14th July 1990. Bob is interested in the Mona Lisa. Likewise, you can connect subjects and objects using predicate. So semantic triples enable creating both implicit and explicit relationships between subjects and objects. And semantic triples also support rich semantic queries and semantic reasoning for information retrieval and validation of requirements. We can model blockchain transactions as semantic triples while preserving cohesiveness of private and public information. That's the main focus in this research. And if I talk about methodology, this paper uses semantic triples and introduces the triples for transaction model. We define a transaction T1 using the T40 model, simulate the transaction flow using Hyperledger Fabric for the defined T40 transaction and the T1 transaction, then compare the transaction flows for number of transactions and cohesiveness of transaction information, and simulate and compare an auditing scenario for both T40 transaction and the T1 transaction. If I talk about our triples for transaction model, this has 5 main classes: transaction, private, ledger, transaction hash, and private hash. So private class, you can define private information between participants. The ledger, you can define public information which is common to all the participants in the blockchain network. And the transaction hash, that's the hash of the content of the complete transaction. And the private hash, so you can have private hashes of private information which you share between participants. So I define this model using ontology web language. So the transaction hash is between the transaction class and the transaction hash class, transaction hash class, and public info is between the transaction and the ledger, so this is private info. Likewise, I define that is public info. Similarly, I define private info and private info hash. And this diagram shows the realization of our transaction T1. The T1 is we define T1 as P1 sends a commodity to P3. P1 sends a commodity to P3 through P2, and there are private information between these participants. There are private information between P1 and P2, and there are private information between P1 and P3 as well. So this is the transaction T1. So T1 has private information between P1 and P2, and this has private information between P1 and P3. And this is the hash of this private information. This is the hash of this private information, and this is the public information which you can find in public ledgers of all the peers. And if you consider this record, T1 P1 T1H and P1 T1 P2 is recorded on the private data stores of P1 and P2, and this one P1 T1 P3 T1 and P1 T1H, this one is recorded on the private data stores of P1 and P3, and the public information, that's the metadata of the transaction, the overall hash of the private keys, private information, and the public information. This record is recorded on the public ledgers of all the participants. There's something which is very important here, that is when I record private information, so I record this overall hash. So you can see this overall hash in these private stores and also on the public ledger, so then you can easily connect this private data private record with the public transaction. And if I talk about the transaction flow in Hyperledger Fabric, so we have this T1, P1, T1H, P1, T1L, that's the public information, the hash of two private and sensitive information. So this record is sending from peer 1 to all other peers as a transaction. Then these peers simulate this transaction with the current the world state and put endorsements and sending the transaction back to the sending peer, that's P1. Then P1 verifies endorsements and sending this transaction to the orderer service to do necessary ordering. In the meantime, P1 is sending private and sensitive information to relevant peers P2 and P3. Then at the ordering, the orderer verifies transactions, orders transactions and create blocks and sending them to all the peers. Then at all the peers, they simulate transactions and check the world state and update their ledgers with the latest block. In the meantime, if they have private information, so they commit their private and sensitive information to their private data stores. So as I said earlier, in their private record, they still have this common hash. So they can, at any time, they can retrieve this private record and connect that with the public record. And if I consider an auditing scenario, P1 T1H is hash of T1, two private hashes and the public information, and auditor needs to check the authenticity and audit private information of P1, T1, P3 at P3. Let's take this as a scenario. So in this case, auditor generates a new hash from P1, T1H, read the public transaction, generate a new hash P1, T1H with this new hash, and then compare the generated hash with the hash which is recorded on the blockchain. However, this process needs reading only one transaction from the public ledger. So if you consider Hyperledger Fabric, so it needs to read, auditor generates a new hash for P1, T1, P3, then read the public transaction, read the private transaction. So this is recorded, this information, the hash of this is recorded as a new transaction on the Hyperledger Fabric. So it needs to read that transaction. So compare hash values of private information. What is important here is this process needs reading two transactions from the public ledger. This is just to audit a single data point from P3. That is, if you use Hyperledger Fabric, you create two transactions and read two transactions when you need to do auditing, and here you create only one transaction. Likewise, when you have number of members, large number of members, and if you have a private and sensitive information to be shared between different members or different sets of members, the number of transactions will go high like this in Hyperledger Fabric. And if you follow our proposed approach, so you have only a single record. You can use only a single record at any time. When you need to do auditing, you just go through the transaction cycle, read only a single record. But if you use Hyperledger Fabric, then again you need to read many number of transactions when you need to do auditing. And conclusion, our T40 model can model both public and private information of blockchain transactions. The proposed model reduces the number of transaction cycles on the blockchain for a transaction which has both public and private information. And the proposed model improves the cohesiveness of transaction information which is needed for auditing, regulatory activities, etc. And this approach supports point-to-point sharing of sensitive information while preserving implicit relationships between the private and public information. The proposed model can be adapted to other blockchain frameworks because the transaction modeling and private data stores stay outside of the blockchain framework. We are working in extending the proposed approach for traceability and item recording supply chain systems, and also modeling tokens for token-based blockchains. Thank you.